In this presentation, I'll be talking about the variants of RRT star, their advantages and disadvantages over each other, and the different problems each variant is trying to solve. The basic RRT star is a path planning problem given a start and the goal configuration. The problem is to find the optimal collision free path between start and the goal with minimum cost minimum cost in the shortest time possible. There are many applications for a path planning problem like RRT star. They are used in autonomous vehicles. Since autonomous vehicles are mostly non-holonomic models, RRT star is the best option that they can resort to. And agricultural robots and surveillance robots also use RRT star for their local path planning problems since they have to overcome dynamic obstacles. Manipulators also use RRT in joint space to calculate a collision free path from start joint configuration to goal joint configuration. RRT star has a lot of advantages over other path planning algorithm. So like RRT star is a sampling based algorithm. They perform very good in high dimensional problems. RRT star is asymptotically optimal, meaning they can find an optimal solution at time equal to infinity. They are also probabilistic complete, which means they can find the solution before time equals infinity. RRT star is easily applicable for models with non-holonomic constraints. They work really well in dynamic environments since points are sampled on the fly. It is an anytime algorithm, which means that it provides solution at any point of time whenever the algorithm is terminated. Coming to the algorithm, this is the basic algorithm of RRT star. The tree is constructed incrementally from the samples drawn randomly from the search space. The sampling is inherently biased to grow towards the goal point. RRT star easily handles non-holonomic constraints. As the points are sampled, the nearest node in the tree is found. If the sample is not sample is not in the obstacle, the tree is steered towards the sample. Once the steering towards the sample happens, we again check if it's in an obstacle or not. If not, then we add it to the tree. This is for RRT. For RRT star, once the steering happens, we check for the nearest nodes of the current sample and see if we can reduce the cost of the path. If that is possible, then we rewire the tree to the newest sample. This steering is one of the important property of RRT star. So this is a visual that depicts the RRT star algorithm. The points are sampled on the fly and the tree explores the entire map. We can observe that the paths in the RRT star are smoothened after the halfway mark, which is not while it is not the case for RRT. Thus, RRT provides an asymptotically optimal path. The rewiring process is the core idea behind RRT star. Once the steering happens towards a sample point, the cost of the nearest nodes are checked and the tree is rewired to smoothen the path and reduce the cost of the prospective paths. RRT star is executed until all the samples are sampled, and yeah. There are issues that RRT has to improve on. The variants that are discussed in this paper mostly solve one or more of the mentioned challenges. The main challenges are slow convergence and large memory requirement. Since RRT star is asymptotically optimal, it stores the expanding tree and it is both slow converging and since this happens, it is both slow converging and it is computationally expensive. Narrow passages are also a nightmare for RRT star. The samples have to be correctly sampled for the tree to expand to the narrow passage. Other than that, the efficiency of the nearest neighbor search, post-processing requirements, and dealing with kinodynamic complexities are some of the issues that we will be seeing in this paper. There are 3 different classification of RRT star variants, and single directional holonomic RRT star is one of them. So anytime RRT star is a single directional RRT star algorithm, it introduces 2 features. Committed trajectories is an iterative strategy where a robot commits to the first step in the path while the rest of the path is optimized. Branch and bound adaptation optimizes the tree for optimal cost. One downside is that it consumes a lot of memory as the tree explores. RRT star FN is another algorithm. Here it samples up to a limited number of nodes. The tree is explored based on these samples. After the threshold, the new nodes are sampled only by deleting the old nodes. The nodes are removed based on node removal policy. Global node removal policy finds a childless node in the entire tree, while the local node removal policy deletes the node with a single child. It requires relatively less memory compared to the original RRT star. As we can see in the picture, we can see that relatively less number of samples have been sampled in RRT star FN compared to normal RRT star. RRT smart is an offline approach. Initial path finding is similar to RRT star. After finding the path is optimized by triangle inequality. A new intelligent sampling method is used based on the biasing ratio. This method improves the convergence rate and provides better cost and time efficiency. However, rate of the exploration is not on par. RRT sharp uses 2 processes. Exploration is one of the processes in which it is an extension process, while exploitation is a global planning procedure to keep track of promising nodes. Promising nodes here are the nodes that might give us good path, and the algorithm prioritizes promising nodes and plans path accordingly. The result is fast convergence. Inform RRT star reduces the sample base based on the current tree. Once a path to the goal is found, it explores only inside an elliptical configuration space. The ellipse is calculated based on start and goal positions. The ellipse size reduces as the path gets optimized. Finally, it becomes a line. So this significantly reduces the search space. This is one of the advantages of our inform RRT star. Now we'll look into another approach. This approach is bidirectional holonomic approach. So RRT connect is one of the bidirectional exploratory approach. Here it generates 2 trees simultaneously from start and goal. These 2 trees explore the sample space and connect when they come near enough. There are a few drawbacks to this method. Neighboring rewiring is in the 2 trees requires high computation. Like for one tree, it already required good amount of computation, but for 2 trees, it's going to be double the amount. And it also results in slow convergence for non-holonomic problems. So bidirectional RRT star, on the other hand, provides empirical results. They reject samples with admissible heuristics. This removes suboptimal samples from the trees. This leads to good convergence rate for non-holonomic problems. Optimal BRRT star introduces multiple heuristics based on different conditions to increase the convergence rate. However, multiple heuristics can cause computational overload. Also, biased heuristics interfere with the algorithm characteristics. IBRRT star introduces intelligent sample insertion heuristic with minimal memory requirement. It improves path quality compared to RRT star and BRRT star, but its application needs further investigation for online planning. HARRT star presents human robot interactive planner using RRT star and homotopy algorithm. It offers a trade-off between computational efficiency and path quality of the computed path. However, natural language processing or graphical user interface could be adapted for compatibility and usability and overload. So the final classification mentioned in this paper is non-holonomic and kinodynamic approach of RRT star. Non-holonomic robots are car-like robots which have to perform complex motion to achieve a particular motion. This phenomenon also restricts geometric path between one point to another point. The vehicle needs to change its position in order to rotate around. Non-holonomic planning requires satisfying both internal and external constraints, hence it's a little more complicated to calculate compared to the previous approach. Spline based RRT star based on cubic curve is based on cubic curve. It presents geometric collision and dynamic feasibility function that checks constraints during expansion. It also provides feasible and cost optimal path in 3D simulation that they evaluated on. However, online planner with real-time application would improve the efficiency of the algorithm much more. RRT star I provides an predictable and practical trajectory generation functionality. This helps in calculating smoother trajectories compared to RRT and RRT star with improved path quality. It also introduces new local sampling techniques. Sometimes it could produce unexpected collisions under high uncertainty with a big, which is a big drawback. PRRT star addresses the problem of high memory consumption and slow convergence by incorporating artificial potential field in its approach. Considering optimal results with fast convergence than RRT star, approach should be tried online in the future. RT or plus C star CS uses local planet to generate feasible paths for car-like robots using circular arc and straight segments. Downside is the generated paths are not curvature continuous and natural. It also results into lower computational performance. DT-RRT star addresses kinodynamic planning for high-speed robots. Instead of rewire, reconnect ray functionality is introduced to have a child with reduced cost. However, reconnect is beneficial only in known environments. Mitsubishi RRT star addresses the problem of continuous curvature smooth path for autonomous driving vehicles. It introduces a new local planner for obstacle avoidance, but uncertainty of dynamic environment is not managed enough. CA-RRT star addresses the problem of large number of samples by using tooth trees and cost entropy. Drawback is it produces energy efficient path in high dimensional space. Energy inefficient path in high dimensional space. Rabbit star uses informed global technique BIT star with RRT star to find the optimal path for narrow passages in high dimension. Local optimizer suggested by the approach needs further improvement. So these are the variants that the paper studied, and thank you.